Welcome. Today we're diving into the world of space complexity and algorithms. When we talk about algorithms, we often focus on how fast they run, but it's just as important to consider how much memory they use. Space complexity helps us understand and measure the amount of memory an algorithm needs to solve a problem, including both the input data and any extra space required during execution. By the end of this video, you'll have a clear grasp of what space complexity means and why it matters in computer science. Space complexity isn't just a theoretical concept, it has real-world implications. Imagine running an algorithm on a device with limited memory, like a smartphone or an embedded system. If the algorithm uses too much memory, it could slow down, crash, or even fail to run. Efficient memory usage is crucial for performance, scalability, and cost. That's why understanding space complexity is essential for developers and engineers working on practical applications. Let's define space complexity more formally. Space complexity of an algorithm is the total amount of memory space required by the algorithm to run to completion. This includes the memory for input values, variables, data structures, and function calls. It's typically expressed as a function of the input size, often using big O notation. By analyzing space complexity, we can predict how an algorithm will scale as the input grows. You might be wondering how space complexity differs from time complexity. While time complexity measures how long an algorithm takes to run, space complexity focuses on the amount of memory it consumes. Sometimes, optimizing for speed can increase memory usage and vice versa. Striking the right balance between time and space is a key part of algorithm design, especially for resource-constrained environments. Algorithms use memory in two main ways, for input data and for auxiliary space. Input space refers to the memory needed to store the input values themselves. Auxiliary space is any extra memory the algorithm needs to process the input, such as temporary variables, data structures, or recursion stacks. When we analyze space complexity, we often focus on auxiliary space, since input space is usually fixed by the problem. To express space complexity, we use big O notation. This mathematical notation describes the upper bound of an algorithm's memory usage as the input size grows. For example, O1 means constant space, On means linear space, and On2 means quadratic space. Understanding big O helps us compare algorithms and choose the most efficient one for a given problem. Algorithm with O1 space complexity uses a fixed amount of memory, regardless of the input size. For example, finding the maximum value in an array can be done with just a few variables, no matter how large the array is. Constant space algorithms are highly efficient in terms of memory, making them ideal for environments with strict memory constraints. On space complexity means the algorithm's memory usage grows linearly with the input size. For example, copying an array or storing all elements in a new data structure requires memory proportional to the number of elements. Many algorithms, especially those that need to store or process every input item, fall into this category. Some algorithms require memory that grows with the square of the input size, known as On2 space complexity. This often happens when using two-dimensional arrays or matrices, such as in dynamic programming solutions for certain problems. Quadratic space can quickly become impractical for large inputs, so it's important to be aware of when this occurs. Auxiliary space is the extra memory an algorithm needs, not counting the input itself. For example, if you sort an array in place, the auxiliary space is minimal. But if you create a new array to hold sorted values, the auxiliary space increases. Analyzing auxiliary space helps us optimize algorithms for memory efficiency. It's important to distinguish between input space and auxiliary space. Input space is the memory needed to store the input data, which is usually unavoidable. Auxiliary space is the additional memory the algorithm uses during execution. When we talk about optimizing space complexity, we're usually referring to reducing auxiliary space. Place algorithms are a great example of space-efficient solutions. These algorithms modify the input data directly, using only a constant amount of extra memory. For instance, revering an array in place requires just a couple of variables for swapping, regardless of the array's length. In-place algorithms are highly valued for their minimal memory footprint. Recursive algorithms can have significant space complexity due to the call stack. Each recursive call adds a new frame to the stack, consuming memory. For example, calculating Fibonacci numbers recursively can lead to deep recursion and high memory usage. Understanding the space impact of recursion is crucial when designing algorithms. Dynamic programming algorithms often use tables or matrices to store intermediate results, which can increase space complexity. For example, solving the longest common subsequence problem typically requires a two-dimensional array. While this approach can save time, it may use a lot of memory, especially for large inputs. Often there's a trade-off between time and space complexity. For example, storing pre-computed results can speed up an algorithm but requires more memory. Conversely, recalculating values saves space but takes more time. Understanding these trade-offs helps you make informed decisions based on your application's needs and constraints. Sorting algorithms vary in their space complexity. For example, bubble sort and insertion sort are in-place algorithms with O1 auxiliary space. Merge sort, on the other hand, requires On extra space for merging. Choosing the right sorting algorithm depends on both speed and memory requirements. Searching algorithms also differ in space usage. Linear search and binary search typically use O1 space as they don't require extra storage. However, more advanced search algorithms like those using hash tables or trees may require additional memory for data structures. Understanding these differences helps you select the best approach. Graph algorithms can have high space complexity, especially when representing large graphs. Adjacency matrices use O(n)2 space, while adjacency lists use O(n plus m, where n is the number of nodes and m is the number of edges. Choosing the right representation can significantly impact memory usage. Recursive algorithms use the call stack to keep track of function calls. Each call adds a new frame, consuming memory. For shallow recursion, this isn't a problem, but deep recursion can lead to stack overflow. Tail recursion and iterative solutions can help reduce space complexity in some cases. Tree algorithms like traversals can have varying space complexity. For example, in order traversal of a binary tree uses OH space, where h is the tree's height due to the recursion stack. Algorithms that store all nodes like breadth-first search may use space. Understanding these patterns helps optimize tree operations. Hash tables are powerful data structures, but they require extra memory to store keys and values. The space complexity is typically where n is the number of elements. While hash tables offer fast lookups, their memory usage can be significant, especially for large datasets. String manipulation algorithms can have varying space complexity. Simple operations like revering a string in place use O1 space, while creating new strings or using additional data structures can increase memory usage. Efficient string handling is important in applications like text processing and search. Arrays are fundamental data structures and many algorithms use them. Copying an array requires O(n) space, while modifying it in place uses O1 space. Choosing between in-place and out-of-place operations depends on your memory constraints and performance goals. Linked lists require memory for each node, typically O(n) space for n nodes. Operations like revering a linked list in place use O1 auxiliary space, while creating a new list or using recursion can increase memory usage. Efficient linked list algorithms minimize extra memory wherever possible. Stacks and queues are linear data structures that require O(n) space for n elements. Algorithms that use these structures, such as breadth-first search, need to account for their memory usage. Efficient implementation and careful management help keep space complexity under control. Heaps are specialized tree-based data structures used in algorithms like heap sort and priority queues. They require O(n) space for n elements. While heaps are efficient for certain operations, their memory usage should be considered when working with large datasets. Sets and maps are collections that store unique elements or key-value pairs. Their space complexity is typically where n is the number of items. While they offer fast operations, their memory usage can add up, especially when storing large amounts of data. When analyzing recursive algorithms, recursion trees can help visualize space usage. Each branch represents a function call, and the depth of the tree indicates the maximum stack space needed. This visualization aids in understanding and optimizing recursive solutions. Divide and conquer algorithms like merge sort and quicksort often use recursion and extra memory for subproblems. Merge sort, for example, requires O(n) auxiliary space, while quicksort can be implemented in place with O log n stack space. Understanding these differences helps you choose the best approach for your needs. Backtracking algorithms, such as those used for solving puzzles or combinatorial problems, can have high space complexity due to the recursion stack and storage of partial solutions. Efficient pruning and careful management of state can help reduce memory usage in these algorithms. Memoization is a technique where results of expensive function calls are cached for reuse. While this can greatly speed up algorithms, it increases space complexity, often to O(n) or more depending on the number of unique subproblems. Use memoization wisely to balance speed and memory. Caching is similar to memoization but often used at a broader system level. By storing frequently accessed data in memory, systems can reduce computation time but at the cost of increased space complexity. Effective cache management is key to balancing performance and memory usage. Streaming algorithms process data in real time, often with strict memory constraints. They use clever techniques to summarize or approximate results using limited space, sometimes as little as O1 or O log n. These algorithms are essential for handling large-scale data streams efficiently. When data is too large to fit in memory, external sorting algorithms are used. These algorithms minimize memory usage by processing data in chunks and using disk storage. The space complexity is determined by the size of the chunks that can be loaded into memory at once. Parallel algorithms run multiple tasks simultaneously, which can increase space complexity due to duplicated data or communication buffers. Efficient parallel algorithms carefully manage memory to avoid unnecessary duplication and ensure scalability across many processors. In real-world systems, space complexity directly impacts performance, scalability, and cost. Applications like databases, web servers, and mobile apps must be designed with memory efficiency in mind. Monitoring and optimizing space usage is a key part of system engineering. Measuring space complexity involves analyzing the memory used by variables, data structures, and function calls as the input size grows. Profiling tools and careful code review can help identify memory bottlenecks and opportunities for optimization. Optimizing space complexity often involves choosing efficient data structures, reusing memory, and avoiding unnecessary storage. Techniques like in-place modification, iterative solutions, and data compression can help reduce memory usage without sacrificing performance. Common pitfalls include unnecessary data duplication, memory leaks, and inefficient data structures. These issues can lead to excessive memory usage and degraded performance. Regular code review and testing are essential to catch and fix space-related problems early. Big data applications process massive datasets, making space complexity a critical concern. Algorithms must be designed to handle data that exceeds available memory, often by using streaming, batching, or distributed processing techniques. Embedded systems, such as those in IoT devices, have strict memory limits. Algorithms for these systems must be highly space-efficient, often using constant or very low auxiliary space. Careful design and testing ensure reliable operation within hardware constraints. Cloud computing platforms offer scalable resources, but memory usage still impacts cost and performance. Efficient algorithms help reduce cloud expenses and improve application responsiveness. Monitoring and optimizing space complexity is essential for cloud-based solutions. Mobile apps run on devices with limited memory, making space complexity a top priority. Efficient algorithms ensure smooth performance and prevent crashes. Developers must carefully manage memory, especially when handling images, media, or large datasets. To wrap up, space complexity is a fundamental aspect of algorithm analysis. It helps us understand and optimize memory usage, ensuring efficient, scalable, and reliable software. By mastering space complexity, you'll be better equipped to tackle real-world challenges in computer science and software engineering. Now that you have a solid understanding of space complexity, you can apply these concepts to analyze and improve your own algorithms. Keep exploring, keep optimizing, and remember that efficient memory usage is just as important as fast execution. Thanks for joining this journey into the world of algorithm space complexity.